Welcome to Demystifying Laser Diode Drivers. I'm Bob Schmidt with Directed Energy Incorporated. We'll cover the topic in 3 parts. In part 1, we'll review Ohm's law, the difference between a current source and a voltage source, and compliance voltage. In part 2, we'll show you how a simple laser diode driver works. And in part 3, we'll talk more about complex drivers, plus we'll touch on impedance matching and safe operating areas. Greetings from the Applications Engineering Department. Today we're going to talk about current sources, which includes current pulsars and laser diode drivers. One of the things that we need to understand when driving things like laser diodes and LEDs is that these are current-driven devices. Why is that the case? Because they have an optical output power that is proportional to the amount of current flowing through them. The higher the current, the more the brightness, and consequently we use current to drive them and control them as opposed to a voltage. These devices have a constant voltage across them when they're driven, and consequently it doesn't help to try to vary the voltage to vary the brightness. One of the best ways of describing how current sources work is to compare them to a voltage source. And to do that, let's go back to Ohm's law, the most fundamental rule that we have in all of the electrical industry. Ohm's law says the amount of current flowing in a circuit, symbol I, is proportional to the voltage, symbol E, and inversely proportional to the resistance. One way to think about this is water flowing through a pipe. The flow, that's our current, is proportional to the pressure, that's our voltage, and inversely proportional to our resistance. A skinny pipe, or one that has corrosion in it, impedes the flow. It has a high resistance, consequently the flow goes down. A fat pipe that's smooth on the inside, has very little resistance, flow goes up. When it comes to Ohm's law, we can keep 2 of these things steady if the third one moves. For example, if we want to build a voltage pulsar, we hold the voltage steady. The current will follow the resistance. If the resistance varies, the current will vary as well. On the other hand, if we have a current source and we hold the current steady, then the voltage will vary as the resistance. It should be obvious, but let me say it anyway. We can control only 2 out of the 3 elements. It turns out that Ohm's law will always dictate the third one, and therefore in a current source we let the voltage vary, and in a voltage source we let the current vary. We're very used to thinking in terms of voltage sources. 1.5 volt flashlight battery, 9 volt transistor radio battery, 12 volt car battery, 115 volt AC outlet, 230 volt AC outlet for our big electrical appliances at home. These are all voltage sources. We are less used to thinking about current sources, a 1 amp or a 10 amp or a 100 amp current source. Now, as you can see from Ohm's law, if we need a certain amount of current to flow and we've picked the resistance, we need a voltage to force that current. The amount of voltage that we need to force a given current through a given resistance can be referred to as compliance voltage. And the important thing is that we have sufficient compliance voltage. When you pick a laser diode from a catalog, you are picking the resistance in effect. That part has been set by the manufacturer and the characteristics of that laser diode. You can also decide how much current to force through the laser diode. It may be 10 amps. That will dictate the voltage. We don't get to say we are going to drive this many volts and this many amps because the voltage will be dictated for us. In the specification sheet, you will see this symbol V sub F, or forward voltage drop. That is the laser diode's characteristic forward voltage drop, and the only thing to remember about that is we have to have a laser diode driver that has at least this much compliance voltage. If this number, for example, is 4 volts, which is common for a single junction laser diode, then we need to make sure that our laser diode driver can source at least 4 volts, or its compliance voltage is at least 4 volts. If we're driving a stack and this number turns out to be 100 volts instead, then our laser diode driver has to be capable of a compliance voltage of 100 volts. It does not mean that there will always be 100 volts coming out of the driver. It simply means that it has 100 volts to work with to drive whatever the current is that we need through our load. In the next part, we're going to be talking about how we generate constant current. A simple way of creating a current source is by taking a voltage source and adding a series resistance. For example, I'm using the symbol for a battery, but this could just as easily be a DC power supply. I'm choosing 100 volts, and I'm placing a resistance of 1 ohm in series with the battery. And I'm going to call this our current source. How does it work? Well, let's try, first of all, using a short circuit as our load. What's the current flowing in our load? Ohm's law tells us it's 100 volts divided by 1 ohm, or 100 amps. Now let's say I add a little bit of resistance to our load. We'll just pick a value of 1/100 of an ohm to start with. Our total resistance now is 1.01 ohms, which means the current flow is going to be 99 amps instead of 100. Well, that's fairly close. So our current really hasn't changed very much by the addition of this particular load. Let's change the load and make it slightly bigger. How about 1/10 of an ohm? Our total resistance is now 1.1 ohms, and Ohm's law tells us that the current flowing is 91 amps. It's still acting as a current source, which is to say, as our resistance changes, our current stays relatively the same. However, as you can see, we're starting to drop current here. And if we were to put in something like, say, another 1 ohm resistor in the circuit, a 1 ohm load, we would now have 2 ohms, 50 amps of current instead of 100 amps of current, and we are no longer in the vicinity of having a constant current source. But for small changes in load resistance, we can say that this is a constant current source. If I had put another 1 ohm resistor in this circuit, what would it take to create 100 amps? We would need a 200 volt power supply instead of 100 volts. So it's a much different animal at that point. The idea here is that if the load does not change very much, we can use a voltage source and a series resistance to drive current through our load, and it will be relatively constant. Now, there is a couple of issues with this approach. One of them, as you can see, is the fact that if we change the load by very much, we're going to start decreasing the current. The other issue is, consider this power supply. 100 volts, 100 amps, that's 10 kilowatts. This would be a huge power supply, very large, very expensive. Fortunately, we don't always need continuous or CW energy going through our laser diode, so there's a couple of things we can do. For one thing, we can install a capacitor across our power supply, and we can install a switch in series with our output, which means we now will generate pulses rather than CW current. How does it work? Well, when the switch is open, we are simply going to charge up this capacitor. We can assume that the power supply is a much weaker power supply than before, and we show that by putting a resistor in series with our perfect voltage source. This resistor demonstrates that our current is now limited, so this power supply may be only capable of milliamps. It doesn't matter because its job is to charge up this capacitor. The capacitor will drive our load for a short period of time because it's charged up to the same voltage as the battery, and it only has 1 ohm of resistance in it, so it can feed 100 amps through our load, but only for a very short time, and that's because this capacitor will give up its energy over time. So what we do is allow the capacitor to charge up, close the switch, generate current in our load, and then open the switch again. We can get a pulse this way of 100 amps, but for a very short period of time, and that pulse will tend to look something like that. It's going to have a rise time that depends on the switch, which of course will be a transistor or some solid state device. And then almost immediately we lose energy into the load, and so the pulse decays. But we can get a very, very short pulse this way, a very high current, with a similar or a simple circuit by adding the capacitor or capacitor bank and then some kind of a switch to the output. It is still a voltage source and a series resistance. Next, we'll talk about how we build bigger and more powerful current drivers. So what can we do to improve on our simple voltage source plus resistance as far as a current source goes? Well, one of the things we can do is certainly add more capacitance to our system, and that is more capacitors in parallel so that we create a bank of capacitors. The more capacitors we have, the longer we can make that pulse. However, we will still not be able to get CW or continuous current because the capacitors will eventually be depleted of energy, and this power supply is of little use to us because it's not capable of generating, let's say, 100 amps or whatever our goal is. After all, it has internal resistance, which is limiting the amount of current that it has. So we're going to have to use some other schemes to get pulses that are much, much longer than this. And one of the things we can do is build a DC-DC converter. It would be a bit more complicated than we would want to draw here, but it's essentially an inductor storage device that creates a constant voltage input to a constant voltage output. Key to any of these schemes is this. We're going to want to monitor the output current. What we typically do is put a small resistance in series with the output and look at the voltage being created by the current flowing through that resistor. That is feedback information which is sent to a control circuit. We create a control loop which keeps the output current constant. So this will feed some sort of control circuit which will vary the voltage so that the amount of current we have flowing through our load, here's our laser diode, stays constant. This type of circuit introduces a small amount of delay in the response, and consequently we don't get quite the same rise and fall times that we do off the other types of circuits. There is another scheme we can use where we want really fast rise and fall times, and it really doesn't care whether we use a capacitor storage circuit or an inductive storage circuit. I'm going to use the symbol for a current source, indicating that however we generate our current, we're going to use a little different scheme to generate the pulses. Here is our laser diode, and we place a switch across the output of our current source. Obviously, it's not a mechanical switch, it's a transistor, a MOSFET. And its job is to decide whether current flows in this small loop here or this large loop. During the time that the laser diode is supposed to be off, we close this switch. The current source now occupies just this smaller loop. The current is flowing through the switch back to the current source. It does not hurt the current source to have its output shorted because, as we saw before, we are controlling the amount of current flow. So whether that flow is through a switch, a short circuit, a laser diode, doesn't matter, it's the same current. So let's assume that the switch is closed. The laser diode sees no current, so it's off. it's actually being protected somewhat by this switch because there are no static electricity forces being induced here. We are basically shorting the laser diode as well as shorting the output of the current source. So our 100 amps flows through this circuit, and now it's time to generate a pulse. What we do is open this switch briefly. We go from zero current to full current, running it through the laser diode through this larger loop. And when we're done and we wish to end the pulse, we close the switch, the current goes back to flowing in the small loop, laser diode goes to being off again, and we end up with rather fast rise and fall periods. This is a very good way of generating very fast rise times and fall times. And if we have a sufficiently large current source, why we can get all the current we want for whatever duration we want. There is another issue that I'd like to bring up that's important on large laser diode drivers when it comes to safety. A lot of our laser diode drivers are controlled by a switch, and we'll just say this is a voltage source of some sort coming out here. When we turn on the switch, we run current through the laser diode, and we get light. If the laser diode is a single junction part, it may have a forward voltage drop of, say, 4 volts, as we mentioned earlier in this presentation. We typically will apply 12 volts or so more than that up here. In other words, our power supply is putting out a total of 16 volts. And all is good. The transistor can be turned off or on and controls the amount of current flow through the laser diode. And when it's time that we want to run a stack or a high voltage type of laser diode here, let's say 100 volts, we then increase the voltage that we put across this output circuit. Let's make it 112 volts. 100 volts gets dropped across the laser diode. The other 12 volts is a housekeeping voltage that we need for our internal MOSFET switches so that they have a little bit of energy to work with. This system also works just fine. However, if we switch back from a stack to a single junction laser diode with a 4-volt drop, and we forget to turn this voltage back down, we now are asking these FETs to drop some 108 volts. At very high currents, we're obviously talking a huge amount of power, and these parts can be damaged. Therefore, it's extremely important when operating with one of these laser diode drivers to pay attention to something called the SOA, or Safe Operating Area Curves. This is a set of curves that's included in the data sheets that tells us what kind of maximum power consumption we can have. It's going to be related to the duty cycle and the voltage that we're driving our laser diode with, because whatever the laser diode does not have dropped across it will be dropped across our switching circuitry, and there is an upper limit to how much power that they can dissipate. One final item, as you have seen in this presentation, we talk about the current source as having a resistance in it that's higher than the load, in order for the load to not have to see very much changes in current. We want that to be constant. When we do something like that, we very often will use strip line cable in this circuit, and it's very important that we watch the amount of inductance in that strip line circuit. So for more information on that topic, please see our webinar on making connections. It addresses this entire issue of very fast pulses and proper hookup. Sometimes when customers look at a piece of strip line, they will think that perhaps we're trying to match impedances and that this is an RF sort of business. We use strip line because we are trying to get maximum power transferred between the laser diode driver and the laser diode. This is not the case. A current source has a high output impedance. A laser diode has a low impedance. We never will get these devices matched. So the purpose of the strip line cable, the heavy duty cable, is to get the most amount of current transferred from the source to the load in the least amount of time and with the least amount of losses. That cable will get warm if there's a large amount of current flowing through it, so we make it thick and wide. We also want to keep the inductance down, and consequently we use techniques that may look like impedance matching, but the fact is we are not. It's strictly a maximum current sort of operation. So, in our webinar we've talked about Ohm's law. We've talked about the need for a current driver as opposed to a voltage driver when dealing with laser diodes and LEDs. We've talked about a simple current source and a more complicated current source. By all means, if you have questions or concerns, get a hold of us. Thank you for your attendance.